Okay, so it's my pleasure to introduce our next invited speaker, Dr. Sam Zukoff. Sam completed his PhD at MIT, where his dissertation focused on reduplication in Indo-European languages, and the dissertation is titled Indo-European Reduplication, Synchrony, Diachrony, and Theory. Since completing his PhD, Sam has continued working on topics in both phonology and morphology, on topics such as copy epenthesis and morpheme ordering, among many others. And all of these are in line with answering this question of what do we really need in our models of phonology and morphology. And Sam's work on these topics has been published in places like NLLT, Indo-European Linguistics, and Linguistic Inquiry, to name a few. Sam is currently a postdoctoral researcher at Leipzig University and is part of the Interaction of Grammatical Building Blocks research group, where he's continuing to investigate these theoretical questions. And today, Sam will be talking to us about reduplication, but not on Indo-European languages. His talk is titled Reduplication in Ponapean and Tawala, Re-Evaluating Base Dependence. So take it away, Sam.
Thank you very much for that introduction, Connie, and thank you to all the organizers for inviting me. I'm very happy to be here. So indeed, my talk is newly titled Reduplication in Ponapean and Tawala, Re-Evaluating Base Dependence. I re-evaluated the title last week when I realized the topic was going to be slightly, or the conclusion was going to be slightly different than I had thought. Okay, so Ponapean and Tawala, which are both oceanic languages, both display intricate phonologically driven reduplicant shape alternations. These patterns are particularly noteworthy because they have the hallmarks of what's known as base dependence. And in terms of reduplicant shape, what base dependence is meant to mean is a pattern where the shape of the reduplicant appears to crucially depend on information that's present only in the surface reduplicant plus base string. Most theories of reduplication, for example, base reduplicant correspondence theory, are equipped or in fact designed to deal with base-dependent reduplication patterns. On the other hand, morphological doubling theory at least claims to predict the absence of base dependence in reduplication. Haugen and Hicks-Kennard 2011 have claimed that Tawala's reduplicant shape alternations must indeed be viewed as base-dependent and thus resistant to Mdt analysis, but compatible with Brct. And I've recently made similar arguments for Ponapean. Today, what I will show you is that while Ponapean's reduplicant shape alternations do constitute base dependence by any reasonable definition, they in fact are actually amenable to Mdt analysis. And the same argument roughly goes for Tawala, which I have had to move to the appendix for reasons of time, but feel free to ask me about that during the question period. So the way that the argument will go is that by invoking independently argued for technology relating to prosodic constituency, the Brct analysis can be imported more or less directly into Mdt in a way that preserves its base-dependent character and leads to a convergent Mdt analysis. The takeaway is going to be that Mdt's claim that it cannot capture base-dependent reduplicant shape alternations must actually be abandoned, which means that these types of patterns actually will not help us distinguish between Mdt and other theories of reduplication, even though we might have thought they could. Okay, so quick roadmap. In section 2, I'll propose a slightly revised version of my earlier Brct analysis of Ponapean. In section 3, I'll sketch the architecture of morphological doubling theory and show more precisely how Ponapean instantiates base dependence. In section 4, I'll work through what I think is a viable Mdt analysis of the Ponapean data using prosodic constituency, as I mentioned. And this will undermine the claim that base dependence is not predicted by Mdt. Then in section 5, I'll conclude that base dependence, at least in terms of reduplicant shape alternations, may not ultimately be a suitable grounds for distinguishing between Brct and Mdt. And as I mentioned, Appendix A contains my analysis of Tawala, which shows roughly the same thing. And in Appendix B, I show an alternative analysis of Ponapean in Mdt that's maybe more in line with some traditional assumptions. Okay, so we'll start with the Brct analysis of Ponapean, and we'll start with the data. So in Ponapean, the derivative aspect is marked by a prefixal partial reduplication pattern. And this pattern predictably alternates, or the reduplicant in this pattern predictably alternates in length between 1 and 2 moras as previewed with the data in 2. So just a couple of notes first. As you can surely see, the two Mora reduplicants have a variety of segmental shapes. Their distribution is predictable, and there's been plenty of work on this. But this is a big topic and a difficult one, so I am just going to mostly ignore that today and focus just on the distinction between one versus two Moras. And the other thing I should note is that I'm not going to consider vowel initial or syllabic consonant initial forms today. I'm not certain whether my analysis completely accounts for these, but I am pretty sure that the constraints that I propose are at least consistent with the outputs that we find in those cases. Okay, so with that out of the way, what I'm going to argue is that the length alternation can be derived through a relatively simple interaction between stress and phonotactics, building on the analyses proposed by Kennedy. And this will be done using constraints whose domain of evaluation happen to span the base and the reduplicant in this particular case. So in order for this analysis to work, the module of grammar where the length and the shape of the reduplicant is calculated must have access to the properties in 3. So it must have access to the surface properties of the base, and it must have access to the reduplicant's position relative to the base. And this is precisely what is intended by Inglis and Zoll's notion of base dependence. In this section, I'm going to lay out my analysis based on the analysis I proposed in that 2020 Nels paper. And it is lightly couched in BRCT, but there's not actually much BR in that. So it is probably compatible with other constraint-based theories that allow for base dependence. Okay, now as a preliminary, I'm going to tell you about stress and accent because that's going to be important to the analysis of reduplication. So the only description of stress and accent in Ponapean that I know of comes from a short passage in Reg 1993, where he says that high pitch occurs on the penultimate mora, while primary stress is on the final mora, secondary stress occurs on alternate preceding morae. Now I'll assume that we can simply scale up from this short description, but I should note that these facts really do deserve further field work to verify. I think this is a good audience to suggest that too. I think you could probably go and solve some of these questions. And so throughout the paper, I will assume, with one exception that I'll mention, that stress is simply algorithmically assigned according to this characterization. So note that in the grammar, Reg and Zoll 1981, they do not mark stress. So this is these are based on those assumptions. I'll be abstracting away from the tonal realization and focusing purely on the position of stress, because that seems to be what determines the things we're interested in. Doing so, we can summarize the stress pattern as in 5, which is that we have primary stress on the rightmost mora and right to left alternating secondary stress by mora. And while you could do this with foot-based constraints, I'm going to use foot-free constraints, the ones in 6. So stress right mora says assign a violation if the final mora is on stress. This will account for 5A. And then star clash mora and star lapse mora will account for 5B, which say respectively assign 1 violation for each sequence of 2 stressed or unstressed moras. So this will be responsible for the alternating, strictly alternating nature of the stress pattern. And just to note that final consonants are non-Moraic, but medial coda consonants are Moraic, and that will be significant. So the preliminary takeaway that you should get from these stress facts are that the strictly alternating rhythm means that the stress status of the initial mora of a base is directly dependent on the Moraic length of that base. So odd mora count bases will have stress on the initial mora. Even mora count bases will have no stress on the initial mora. Their leftmost stress will be on the peninitial mora. And this will help us explain what's going on in reduplication. Okay, so now back to the data. So Kennedy, 2002 and 2003, building on earlier work by McCarthy and Prince, shows that considerations of stress and syllable weight in the base factor into determining the length of the reduplicant, length being calculated in terms of moras. And what I'm going to argue is that reduplicant length is explained entirely by looking just at the stress and the weight of the base initial syllable. So this is a slight refinement of Kennedy's analysis. We can begin to see how this works by arranging the data in terms of the Mora count of the base and the Mora count of the reduplicant, as shown in 8. And this chart is based on similar charts in Kennedy. Just a note about this data, the way that I'm assigning stress, this is where we can see the exception to the alternating stress rule. In my earlier paper, I assumed that the 2 Mora reduplicants to even Mora count bases, these 2 gray squares, that they had stress on the second Mora of the reduplicant, which is what we'd expect by blindly applying Raig's stress algorithm. But today I'll be assuming, following Kennedy, that these forms instead have stress on the first Mora of the reduplicant, and this will bring the BRCT analysis more in line with what we'll have to say about the analysis in MDT. But do note that my BRCT analysis is consistent with second Mora stress here, but the MDT analyses will have more trouble with that. They might be able to get it, but it would involve some sort of ad hoc opacity. So this is one of the empirical questions that deserves further investigation. Okay, so now let me tell you what's going on in the data. Unfortunately, it is separated from the generalizations more than I would like, but hopefully you can follow along. So one of the generalizations that emerges when we look at the Mora count of the base is that odd Mora count bases always have 2 Mora reduplicants, but even Mora count bases can have either 1 Mora or 2 Mora reduplicant. So the odd cells here, odd length cells here, they always have 2 Moras, 2 Mora reduplicants, but the even ones, they always have, or they alternate between 1 and 2 Moras. But recall that stress is strictly alternating from right to left by Mora, which means that odd Mora count bases always have initial Mora stress, and even Mora count bases have pen initial Mora stress. So we can reframe these generalizations in terms of stress, simply as bases with initial Mora stress always have 2 Mora reduplicants, and bases with pen initial Mora stress can have either type. Now, focusing on the even Mora count ones, that is the pen initial Mora stress ones, these are extracted in 11. There is a consistent difference that determines which reduplicant length occurs. So if the base has an initial light syllable, that's the second row here, it always has a 2 Mora reduplicant. The initial syllable here is bolded, not the reduplicant. But if it has an initial heavy or super heavy syllable, it always has a 1 Mora reduplicant. Okay, so those are the main generalizations. There's one more that will help us, which is that all reduplicants bear a stress on their leftmost Mora, at least by hypothesis. So we can clearly say that all reduplicants have a stress, and modulo the question I raised earlier, it does seem that they're all on their leftmost Mora. Okay, so now I'll start moving into the analysis, and I kind of preview it here with the core components, of which there will be essentially 4. The first is a preference for shorter, by which I mean monomoraic reduplicants. The second is a requirement that the reduplicant bear stress on its first Mora. Third is the ban on moraic clash, and the fourth is a ban on adjacent identical light syllables. And I'll go through these one by one now. So the preference for shorter reduplicants, I'm going to motivate this with the size restrictor constraint align root left. This is couched within Hendrick's compression model. I'll read this out for you. So the constraint align root left, I'm going to define as assign 1 violation for each timing slot, which intervenes between the left edge of the root and the left edge of the word. The use of timing slot as a unit of alignment is a little unusual, but this will simplify things by allowing us to treat long vowels, diphthongs, and short vowel plus consonant rhymes all equivalently, which is something that we'll need for the analysis to work. And then in order to actually effectuate the preference for shorter reduplicants, align root left must outrank max BR, the constraint which prefers maximal copying into the base, and the ranking there is shown in 17. Max BR won't actually be doing anything, so I will leave it out of most of the tableaus. The second part of the analysis is the requirement that reduplicants bear stress. And I'll enforce this via the constraint stress left red, which says assign one violation for each reduplicant whose leftmost mora is not stressed. So this is very specific. Maybe we could reduce this to independent factors, but we'll see that it has an avatar in the Mdt analysis that might be more familiar. So this is the only context, like I said, where morae stress lapses can occur, and therefore we'll need this constraint to outrank star lapse mora, which was one of the constraints we needed for the stress pattern. And we'll see how all these interactions work once we get to the actual data. Okay, the third piece is the ban on morae clash. This will follow from the same star clash mora constraint that we needed for the basic stress pattern, which simply says avoid two adjacent stress moras. When we combine this constraint with the effective stress left red, this is going to motivate reduplicant extensions for bases with initial stress. So maybe you can see where I'm going with that. The last piece is a ban on adjacent identical light syllables, which I will encode pretty directly with the constraint star repeat light, which says assign one violation for each sequence of two adjacent identical light syllables. This is inspired by Hicks-Kennard's analysis of Tawala, where she uses a similar constraint. And this is what's going to motivate reduplicant extension for bases with initial light syllables. So the crux of the analysis is going to look like 22, where these last three constraints, stress left red, star clash mora, and star repeat light, all outrank the size restrictor constraint align root left, and some of them will also outrank star lapse. So the takeaway that you can get from this sort of overview is that the combined effect of these constraints can override the preference for short reduplicants, yielding otherwise dispreferred two mora reduplicants for particular base shapes. So now I'll show you how all of this works. So there's essentially 3 or 4 cases, depending on how you count it, that I'll go through one at a time. The first will be one mora reduplicants to even mora count bases. This will be the default case, according to the analysis. Then I'll go through the 2 mora reduplicants to odd mora count bases, which are extended by the stress constraints. And lastly, the 2 mora reduplicants to light syllable initial bases, which are extended by the star repeat constraint. There will be a subtype of 23C that is of interest, the ones where bases contain repetitions inside of them. Okay, so let's go through these one at a time. So when stress left red, star clash mora, and star repeat light can all be satisfied, the default preference for a monomoraic reduplicant is actualized. But this only happens when 2 conditions are met simultaneously. The first is that the base has an even number of moras, such that the leftmost base stress falls on the base's pen initial mora. And the second is that the base begins with a heavy or super heavy syllable, such that a monomoraic reduplicant won't yield adjacent identical light syllables when it's concatenated with the base. And that will be a somewhat important notion as we proceed. And here again is the data of this type of base, where we have even mora count bases with heavy initial syllables. They all have 1 mora reduplicants. And I will illustrate the analysis with the example in 26, but first just a note on the candidates, which I try to use fairly consistently throughout the section. They essentially fully cross 2 variables. One is the length of the reduplicant, 1 mora versus 2 mora. So the first 2 candidates have a 1 mora reduplicant. The second 2 candidates have a 2 mora reduplicant. And the other is whether or not they have initial stress. The A and C candidates do not. The B and D candidates do. Okay. So you can keep that in mind as we go. So in this case where we have a single syllable base that has a long vowel, none of these 4 candidates will violate star clash because the base initial mora is unstressed. None of these candidates will violate star repeat light because the base initial syllable is heavy, so we're never going to get a light syllable on that side of the juncture. And then candidates 26A and 26C, these are the ones that don't stress the reduplicant initial mora. these will fatally violate stress left red, right? So this is a monomeraic reduplicant that doesn't have any stress. This is a bimeraic reduplicant that has second Mora stress. So both of those will equally violate stress left red in its current formulation. So these candidates, the A and C candidates, will essentially be non-starters throughout the analysis because they will always violate stress left red. So this leaves us with 26B and 26D as the ones that satisfy all of the top ranked constraints, and I pull them out here in 27 so we can see what happens next. So the longer, the 2 Mora reduplicant in 27D does worse on both of the lower ranked constraints, star lapse Mora and align root left. So it has a lapse across the juncture, so it violates this constraint. And it has 3 timing slots to the left of the root, so it violates align root left 3 times, whereas the monomeraic reduplicant with just the initial C and short V violates align root left twice and does not have a lapse. So it does better on both of these constraints. And so these constraints will select the shorter reduplicant, in this case, the stressed monomeraic reduplicant. So this is essentially what happens when all of the high rank constraints can be satisfied. This is what the system wants to do. It wants to have a short reduplicant. Okay, but when we move to odd Mora count bases, these stress considerations essentially flip. So the strictly alternating rhythm places a stress on the first Mora of the base. In monomeraic bases, this will be a primary stress. In longer bases, it will be a secondary stress. This difference doesn't matter for these purposes. And so some representative data is shown in 28, where we can see that these always do have 2 Mora reduplicants. And again, I'm collapsing over different base or reduplicant shapes and just focusing on the length. And maybe it's worth mentioning that, again, that medial coda consonants are moraic. So this N here does count as a Mora. Okay, so now crucially, since we have odd Mora count bases, and we now have base initial stress, the stressed 1 Mora reduplicant 29B, which is the one that won in the previous case, this incurs a star clash Mora violation because we have stress in the reduplicant followed by base initial stress. This will be a problem that we need to fix. And we could fix the problem by not stressing that monomeraic reduplicant, but this again will violate stress left red. So that's not going to help. And 29C is still a non-starter. It will in fact violate both of these constraints this time. So what we can see is that as long as stress left red and star clash outrank align root left, it will be better in this case to tolerate the longer reduplicant, that is the 2 Mora reduplicant in 29D with initial stress, than to mess up the stress pattern, essentially. So you want to satisfy all the stress constraints, and that that motivates changing the length of the reduplicant away from what it wants to be. So again, this shows that the reduplicant is extended to 2 Moras in case it can optimize the stress pattern. And then just a few technical details that you can zone out if you're not super interested in the details of the analysis. So the language does not diverge from its regular stress pattern in order to coerce the shorter reduplicant, which would give better satisfaction of the line root left. So for example, you don't retract stress on the base in order to avoid a lapse and or get the shorter reduplicant. So we know that stress right Mora dominates on line root left, nor do you get rid of the base initial stress, which would satisfy stress right Mora and better satisfy a line root left, because it will give you a lapse in the middle of the base. So essentially, again, what we see is the shape of the reduplicant is subordinated to the stress constraints. 31 shows that essentially making the reduplicant longer is never going to help, even if you push it all the way out to 4 Moras at the 31D candidate. where the stress pattern continues to be strictly alternating, that will just get you extra violations of aligned group left. So essentially, there's never going to be any reason to extend past 2 moras because either 1 mora or 2 mora will optimize the stress pattern for any given base. The comparison between 31D and 31A also shows why the star repeat constraint must be restricted to light syllables, because we do in fact get a heavy repetition across the juncture, but that doesn't divert us away from that candidate. And we'll get to the star repeat light more next. Okay, so the stress-based account of reduplicant extension does not get us the whole range of 2 mora reduplicants. It predicts that all and only odd mora count bases would have 2 mora reduplicants. But what we find is that we do have 2 mora reduplicants for even mora count bases if that base has an initial light syllable. And this is the data pulled out in 32. So yeah, again, you can see that each of these cases has an initial light syllable. And this effect can be captured with the constraint star repeat light, which I repeat here in 33. This is inspired by work by Moira Yip, but I became aware of it through Hicks-Kinard's analysis of Tawala. This is sort of a syllable size version of the OCP. You can think of it that way. What we will find is that star repeat light will motivate extension to a 2 mora reduplicant in case the base begins in a light syllable. So, right. So again, the relevant comparison is between the B candidate and the D candidate. And it will, so star repeat light will penalize a 1 mora reduplicant, so either 34A or 34B, because that would result in this kind of base in 2 adjacent identical light syllables across the base reduplicant juncture. So just like star clash mora was ruling out the stress monomoraic reduplicant in the previous type, star repeat light is ruling out that candidate just in case there's a light syllable at the beginning of the base. So again, the way that you fix it is by extending the reduplicant out to 2 moras, even though in this case that will result in a clash if we assume, again, that they are stressed on the initial mora. So to summarize what this shows us is that the reduplicant is extended to 2 moras, not only when that would avoid a clash, but also when it would avoid a violation of star repeat light. Okay, again, several additional technical points here. It's important to note that stress must not factor into what counts as identical for star repeat light, because in the B candidate, which we need star repeat light to eliminate, the 2 light syllables differ in stress. So essentially the takeaway is that stress differences do not make syllables not identical for the purposes of this constraint. And Hicks-Kinard makes the same point for star repeat in Tawala. Yes, this is just an additional ranking point, which we can skip. Actually, no, this is important. So aligned root left is going to help us distinguish between different ways of getting to that 2 mora reduplicant. So here you could either copy the final vowel, or you could just copy the medial onset into the coda. And since doing that makes the reduplicant 1 timing slot shorter, that is what is selected by aligned root left. And this just shows that star repeat light also applies in light syllable and initial odd mora count bases, where both star clash and star repeat will motivate extension to 2 moras. Okay, the last point before we move on is that even though star repeat light has an observable effect on reduplicants in Ponapean, the language does not show evidence of sensitivity to this constraint in other domains. So essentially, light syllables are tolerated outside of reduplication, reduplicants in particular, which we can see in bases like the one in, or roots like the one in 38. And we can account for this difference in that it's allowed in roots, not allowed in reduplicants, by having input-output faithfulness constraints outrank star repeat light. So this is a classic emergence of the unmarked effect. And this is worth thinking about because morphological doubling theory will treat TETU in a very different way. So we'll want to be careful with that. Okay, so that was the BRCT analysis. This is the ranking summary. The analysis is conceptually at least pretty straightforward. Reduplicants prefer to be one more along, but they will settle for being two more as long if that allows them to avoid clashes or light repetitions. And this analysis is therefore entirely surface-oriented and transparent, which is maybe a point in its favor, but it doesn't rule out that there could be other analyses and other frameworks. So in the remainder of the talk, I'm going to show that a version of this analysis can, in fact, be implemented in morphological doubling theory, despite its apparent base dependence, which I will spell out now. Okay, so morphological doubling theory works as in 42. The derivation begins with two identical inputs, which feed two distinct derivational nodes. One is the reduplicant, or scare quotes, the reduplicant cophonology. The other is the base cophonology. And by cophonology, we mean a possibly distinct phonological grammar. So they are subject each to their own phonological grammar. It could be the same, it could be different. And in reduplication, they will almost always be different in crucial ways. And the key to note is that these two nodes can't see each other at this point in the derivation. So the outputs of the daughter nodes then jointly form the input to a single derivational node called the mother node. And this again applies its own cophonology, which may or may not be distinct from the others. And this node concatenates the two daughter outputs, which again form its input, and they produce the final output according to the phonology of that node. And it's important to note that in morphological doubling theory, there's no formal equivalent of the concepts of base versus reduplicant. They are all the stuff that gets to the mother node is treated equivalently. So the architecture of MBT sort of straightforwardly seems at least to predict the lack of base dependence. And we can see this when we think about the way that phonology could apply to different morphological constituents. So in this architecture, special phonology can apply to the reduplicant before it sees the base. That would be phonology that's located in D1. Alternatively, special phonology may apply to the constituent that contains the reduplicant and the base if it's in the mother node, but it would apply equally to both of those pieces. But there's no way in this theory, at least on the face of it, that special phonology can apply to the reduplicate once it already sees the base. So if we observe a pattern that truly constitutes this last type of interaction, this should be a problem for MDT. But what we'll see is that if we appeal to prosodic constituents, Ponapean's apparent base-dependent patterns can actually be shoehorned into an MDT analysis that really recapitulates base dependence in the same way that BRCT does. So just a quick review of the BRCT analysis. It hinges primarily on the operation of star clash Mora and star repeat light, which are the constraints that motivate extension of one Mora reduplicants to two Moras. Now for both of these constraints, the structural descriptions encompass sequences, so of Moras and syllables respectively. And in the case at hand, the relevant sequences happen to span the base and the reduplicant. That is to say, a one Mora reduplicant is disallowed if there would be a clash across the reduplicant base juncture and or there would be identical light syllables across the reduplicant base juncture. And we cannot reduce either of these properties, or either of these factors, to properties of the reduplicant in isolation, because light syllable reduplicants and one more stress reduplicants are both allowed and in fact preferred in other contexts. So these properties alone, the properties of the reduplicant in these cases, are not enough to distinguish the cases. And it's also worth noting that since stress is grammatically assigned, the reduplicant must be aware of surface properties of the base, not just underlying ones. So to summarize, what this means is that the module in which reduplicant length is determined must have access to the reduplicant's position relative to the base and the surface properties of the base. This is what Ingles and Zoll mean by base dependence. And this will tell us something important about the architecture of the reduplicative grammar. So this is compatible with a grammar where either the base is computed and then the reduplicant is computed with the base visible, or the base and reduplicant are computed together. And most theories of reduplication have an architecture that looks like one of these, including BRCT, straight LOT, and STS. But on the other hand, it's not compatible with a grammar where the reduplicant is computed first and then the base is computed. I don't know of any such theories, so that's fine. And it's also not compatible with a theory where the reduplicant and the base are computed separately. And that's exactly the type of architecture that MDT has, at least in theory. So if we've characterized Ponapean correctly and MDT's prediction about base independence is correct, then MDT shouldn't be able to generate Ponapean. But what I'm going to show you now is that this is not the case. So what I'm going to show you is that the BRCT analysis can effectively be imported wholesale into MDT by locating the analysis in the mother node, that is the reduplicated word cophonology. And part of the reason why this will work, and works so straightforwardly, is that the BRCT analysis, it doesn't actually rely on any active base reduplicant faithfulness constraints. So the main part of the analysis, the MDT proposal, is that the base versus reduplicant distinction can be recapitulated in MDT by asymmetric assignment of prosodic constituency between the daughter nodes. So faithfulness constraints that reference these prosodic constituents will allow for truncation in the reduplicant without generating truncation in the base, all simultaneously in the mother node. And this distinction will subsume the emergence of the unmarked character of the star repeat light effect. As I mentioned, there's another possible analysis in the appendix, but that's actually not important for this argument because I'm going to be using standard MBT technology. Okay, so I'm running a little short on time, so I might go through this quicker than I would have liked. One of the tools that Ingles and Zoll make extensive use of in their various analyses in the morphological doubling theory book is the notion of prosodic constituents that are associated with but distinct from morphological constituents. So for morphological roots, there's a corresponding prosodic root. Morphological stems have prosodic stems, and while they don't talk about it, I think they mean that morphological words have prosodic words. And they introduced this in their analysis of Javanese, where they appeal to the prosodic root in order to account for why certain affixal segments get copied along with the root in reduplication. So why this glottal stop from the causative affix gets copied along with the root. A quick summary of their analysis is that the stem nodes that feed the reduplicative daughter nodes build prosodic roots that include all the root segments and all adjacent non-root segments that don't add a syllable. So essentially, you can't add any extra syllables, but you add all the other segments that you can. And then crucially, D1 will delete all non-P root segments. So we can get this with a special faithfulness constraint, something like max P root IO, which says don't delete any segments that were in a P root in the input. And if this special max constraint outranks a constraint that motivates deletion in general, like star struck, but that constraint in turn outranks the general max constraint, will delete everything outside of the p root that's in the input to D1, but nothing that is inside the p root. Okay, so this is just a summary, which I will skip. And this technology is not limited to their analysis of Javanese. It's really significant in a number of their analyses, which are major arguments against BRCT, for example. So while these analyses locate truncation or p-root circumscribed truncation in the daughter nodes, we can put that same kind of interaction into the mother node. And that's what I'm going to do for Ponapean. So the daughter nodes in the Ponapean MDT analysis will have the following properties. D2 will build a prosodic root over all of its input material, and D1 doesn't build a prosodic root, crucially, and it assigns a single stress to the leftmost mora, similar to what stress left red was doing in the BRCT analysis. There will be two special faithfulness constraints that are active in the mother node, the max p root constraint that I introduced above, and also a constraint that bans deleting things that were stressed in the input. And while we could use star struck, we can also use an alignment constraint equivalent to our align root left from the BRCT analysis, but instead of the morphological root being aligned, it's the prosodic root that's being aligned. So again, what happens here is that the prosodic root wants to be as far to the left as possible. So it is fully satisfied if you delete the output of D1 entirely, but because there was a stress there, you can't delete that initial CV string, and so you have to keep it, essentially. That's the best you can do on a line p root left. But what you will do is you will delete everything else if you can. But just as in the BRCT analysis, you can't if that would violate star clash mora or star repeat light. So you can't delete the second mora if doing so would lead to a clash. And you can't delete the second mora if doing so would lead to a star repeat light violation. These are more ranking arguments that don't really matter. And this is to say that max p root IO is all we need in order to say that this is a TE2U effect, because just as it blocks deletion in the general case, it will block deletion in a base that violates star repeat light. So essentially, once it's inside the p root, you can't change it, and so it will be maintained by this special faithfulness constraint. Okay, so here's the summary of the MDT analysis. This is the crucial stuff going on in the mother node. Here are some constraints that we could use for the daughter nodes, but those are not super important. What I want to show you is comparing the mother node analysis in MDT to the BRCT analysis that I proposed earlier. These are exactly the same. These are the same exact constraint interactions. All of the crucial rankings are the same. The only thing that is different is the definition of a few of the constraints, which have been changed in order to accommodate the differences between the theories. You can just verify this visually. These are the same Hasse diagrams. Okay, so I'm running out of time, so I'm glad that I have just gotten to the conclusion. So this demonstrates that MDT can actually directly recapitulate the BRCT analysis of Ponapean reduplication by placing most of the action in the mother node. And this analysis only uses technologies that Inkelis and Zoll use themselves, most notably the morphologically related prosodic constituents and faithfulness to that constituency. So since this analysis takes base dependence at face value, that is the ultimate shape of the reduplicant still requires knowledge of the concatenated output string, Inkelis and Zoll's claim that MDT cannot generate base-dependent reduplicant shape alternations cannot be upheld. And this argument holds regardless of whether this is the correct analysis of Ponapean, because the tools that I employed here are all appropriate to MDT. So we predict languages that do work in exactly this way, even if Ponapean for some reason isn't one of them. There's another analysis of Ponapean and MDT that is available to us, so maybe that's better for Ponapean. And similar arguments can be made from Tawala, which is in Appendix A. And also noteworthy is that it shows that TETU effects can in fact be analyzed as such in MDT, where prosodic asymmetries stand in for morphological asymmetries in other theories like BRCT. So the logical conclusions are the ones that are listed in 68. So either we say that Ponapean counts as a base-dependent reduplicant shape alternation, and MDT can account for it. That's basically what I've been arguing. And the logical conclusion of that is that MDT must abandon its predicted claim, or its claim prediction, rather, of base independence, at least in the realm of reduplicant shape alternations. Alternatively, we could simply say that Ponapean doesn't count as a base-dependent reduplicant shape alternation because MDT can account for it, but that reduces the prediction to essentially a tautology. Or we can sort of defer judgment on whether it's base-dependent and reject the MDT analysis based on the way that it uses prosodic constituents, but then MDT would have to abandon a number of its central arguments against BRCT, which are based on analyses of exactly that sort. So I think there's no reason not to accept 68A and embrace the idea that base-dependent reduplicant shape alternations ultimately are not a fruitful ground for distinguishing between MDT and other theories of reduplication. I am out of time, so I will go through this, or I will sort of skip over this. There are other types of base-dependent reduplicant shape alternations based on, again, prosodic constituency. Hagen and Hayes-Kennard say that they argue against MDT, but I think that if you adopt the sort of analysis that I've laid out here, they actually do follow straightforwardly. And what this means is that really the only place where base dependence is in reduplication is a relevant question is in the realm of reduplication phonology interactions, that is things like over or under application opacity, backcopying, recopying, and those sorts of things. And that question is very much a live issue in the literature. That's what a lot of the literature on reduplication, at least the theoretical literature on reduplication, focuses on. And this is maybe a nice thing because many of these debates actually hinge on empirical questions rather than theoretical ones. So they maybe have a better chance of being solved. So my final takeaway is that reduplicant shape alternations do not substantially differentiate MDT from BRCT, so we should keep focusing on reduplication phonology interactions. Thank you.
Thank you, Sam. And we do have some time for questions, so please feel free to use the raise hand function, or you can type it into the chat if you'd like, and I can read it out.
Hi, Sam. I'm sorry. I'm on my phone and I don't know how to raise my hand or whatever is in a little appointment. But I just want to say, I'll look more closely at your handout later and leave you some comments in the Slack. But sorry, I wasn't really able to follow along that well because I was in the middle of an appointment. So, but thank you very much. So I'll be leaving you comments in the Slack.
Oh, thank you very much.
Yeah.
Joe has a question.
So I want to sort of, because I don't know that I fully digested the point that you had at the end about this particular debate, but I wanted to maybe invite you to sort of talk about that a little bit more, right? So as I understood it, right, so part of the issue is this MDT theory makes this prediction that that kind of relationship to the base, that information can't sort of be accessed directly, right? But at the same time, it almost sounds like it's almost sort of a definitional issue, right? If you can restate it in this sort of MDT format, then maybe it doesn't count as having that kind of interaction. But I'm wondering then, is there a particular kind of phenomenon, a certain phenomenon with a particular shape that you think arguably would clearly push us into one side or another? Maybe not from right here, but just sort of, what would that data look like, or what kind of things should we be looking for?
Yeah, so what led me to this project was that I thought this was such a case. I thought that these base-dependent reduplicant shape alternations, I thought MDT's claimed prediction was correct, and so that if Ponapean was what it looked like to me, I mean, so Inglis and Zoll do mention Ponapean and Tawala as two cases that would be relevant. So that sort of led me to be looking into this. And it wasn't really until last week that I realized there was a workable Mdt analysis and that it all fit together in this way. So I thought that this was such a case, and what I came to realize was that it is not. So I'll maybe take another second to talk through the Prosodic constituent copying. So Haugen and Hayes-Kennard, their paper is sort of split up into two. One of it is going through Tawala, where they argue that it is like Ponapean, a base-dependent reduplicant shape alternation where it's essentially junctural information that triggers the alternations. The other type is what they call prosodic constituent copying, or maybe they don't call it that, maybe I'm just calling it that, but that's the idea. But what they mean by it is it's an instance where reduplicant shape co-varies with the syllabification or foot structure of the base. So they give a number of examples, including foot copying in Udine. This pattern always copies two syllables, and whether the second syllable has a coda depends on whether the consonant following the second syllable nucleus in the base is syllabified as a coda or an onset, which is difficult to generate in parallel theories. It's difficult everywhere, I think. But what they show is that, what they argue is that the only way you could get this in MDT is, since you don't have access to the base, the output base, for copying purposes, and that logic does still hold, that you would need to have the syllabification and foot structure in the input in order to account for them. But what they don't seem to be thinking about is that it's well established in MDT that the input to the daughter nodes can be morphologically complex. So, for example, that Javanese instance, it's a built-up causative that goes into each of the daughter nodes. So if you assume that the node that feeds the daughter node can assign syllable structure and foot structure, you can use the same sort of truncation analysis, whether it's in D1 or in the mother node, in order to reduce it down to just what's in that prosodic constituent. So I don't think that this is an argument against MDT based on base dependence. So that leaves us with this, which I only mentioned very in passing. So this is really where the reduplication literature has been focusing since McCarthy and Prince 95. So these are cases where you get the wrong phonological segment or feature or sequence in the reduplicant because of faithfulness to the base, essentially. So faithfulness to derived properties of the base through correspondence in their analysis. And so subsequent theories, they all say that BRCT is too unrestrictive, and their architecture only predicts some subset of those cases. And so they all argue that the data that McCarthy and Prince use to motivate these complicated interactions, they're all wrong for some reason. Either McCarthy and Prince are misunderstanding the data, or the data itself should not be, is not real. So for example, there's this sort of central case in Johor Malay where you have nasalization, you have a nasal harmony rule that ends up putting nasalization, or in reduplication, you end up allegedly getting nasalization in a place that it can't end up by regular application of the harmony rule. This is the recopying case. And so Kaparsky and McCarthy, Kipper, and Mullen, so this is straight LOT and serial template satisfaction and harmonic serialism. They can't generate that pattern. And so they say, well, actually, we don't believe the empirical reports of that pattern. So that's why I say these are largely empirical questions that sort of a huge amount of theoretical weight hinges on whether the first syllable in a couple of forms has nasalization or not. So someone should go do field work on Johor Malay. So hopefully that answered your question in a very long-winded way.
Thank you.
Kenyon has a question.
Yeah, so thanks for the talk. I had a question about 68 and the box below it. Did you see reason to not accept 68B or 68C?
So, well, I think that B is reasonable, but it then voids the theory of any content or the prediction of any content. So it's not very interesting. And C, I mean, I think that it does count as base dependent by any reasonable definition. So there's no reason to do this. I actually don't like this technology. So as I said, I came into this trying to argue against MDT. But as I reread through Inkelas and Zoll, they adopt this stuff wholeheartedly, and it's crucial to their analysis against certain opaque reduplication phonology interactions like I was just talking about. So it's not some peripheral thing to their theory, it really is crucial. So if you wanna argue against that, then that sort of is more essential to arguing against MDT. So I think that given that I don't really see too much that's super objectionable about my MDT analysis, I think we probably want to conclude 68A, but this is just the range of things I was thinking about, and I think all of them lead to roughly the same place.
Okay, thanks.
Thanks. I think Josina has her hand up.
Sorry, I think I got cut off there, but yes, we have a couple more minutes. Josina, please go ahead.
Okay, I'll try to be quick. I had a question more specifically related to the Javanese examples. And so I'm not familiar with the paper, but do they have other examples that show the copying effect of other segments besides glottal stop? And the reason I'm asking is because in other affixes in Javanese, you can have glottal stop insertion for phonotactic reasons. So maybe you have comment on this.
Yeah, so I was just using this as a schematic example. So that their analysis is a bit sketchy, as most of the analyses in that book, but they do have plenty of other examples. So there's a locative suffix, I believe, with an initial n that gets copied, and also maybe a nominalizer. There is a nasal prefix, I believe, to the causative construction, which usually gets copied. And that's an initial position.
Yes.
And there are also various kinds of ablaut effects that they say kind of work in the same way. So I think that their analysis, their analysis definitely does not rely on this being a phonotactic thing. There are other cases where you end up with a segment being copied as a syllable coda followed by a syllable onset. So this example is not really the best to show the full extent of the analysis, but it's the one that they use. And
Okay.
yeah.
Yeah,
Okay.
maybe out of those examples, I'd be most convinced by the locative, like the N copying, because I'd be, I think at least with the nasal prefix copying, there might be semantic effects. So then yeah, so I think I would be most convinced with the locative me.
Yeah,
Thanks.
so I was just using this as an illustration. I don't necessarily
thanks for
endorse their
elaborating.
analysis. Yeah, thank you. Yeah, so just to follow up, some of these other languages that I mentioned, they do other things with these prosodic roots that seem more sort of interesting. Yeah.
Great. Thank you so much again, Sam, for that great talk.
Thank you.
Or we can virtually clap. We are now going to take a short break and we'll come back in about 13 minutes.
Thanks, everybody.